Hello and hello. Welcome to February 26, 2019. This is the course 120, Anatomy of the Ear, and we are now in unit, I believe, 4. We're looking at the anatomy of the inner ear. So, anatomy of the inner ear, we are continuing from where we left off last week. We spend 2 weeks on the anatomy of the inner ear, and then we'll spend another 2 weeks on the physiology of the inner ear. As we can tell, it's all about the inner ear, because without the inner ear, you have no ear, okay? So here we go. I'll share screen, and we'll look at our notes first, where we covered last week. Last week, we talked a lot about the membranous and bony labyrinths, talking about the vestibular system in particular, but we said both share the same fluids, both have hair cells, both have endolymph, both have perilymph, and stressing the fact that you've got the bony labyrinths and the membranous labyrinths. And to look at that once again, to make sure we've got it, this would be a picture of the bony labyrinth. Remember, all the white surrounding this is solid bone. If we go to the very first slide here, okay? All the white surrounding here is solid bone. There, the light brown would be the bony labyrinths. The yellow would be the bony labyrinths. The cochlea, the vestibular system. The membranous labyrinths would be the pink in the vestibular system and the orange in the cochlea. We moved along. We talked about the vestibular system last week, and we'll move right through that because we covered that last week. A picture again of the bony and membranous labyrinths, highlighting now the membranous labyrinths in dark gray, and moving on to describe how the membranous labyrinths are highlighted here in the cochlea especially, not simply as a round tube, but more specifically, you can see it as a triangular shape. And this slide really highlighting that triangular shape. So back over to here, bony labyrinth being the light gray, membranous labyrinth being this triangular three-dimensional kind of shape. When you look at it in more detail yet, you can see 3 different chambers. One here, one here, one here. So you've got the oval window, the footplate of the stapes that I'm circling here, scala vestibuli, and pushing the fluid all the way around until it goes down the helicotrema and then back out the scala tympani, right where my arrow is here, going toward the round window. And the scala media in between, which contains the cochlea, or which is the cochlear duct. This is just a picture showing you again just the membranous labyrinths. You can see all the nerve fibers leaving the membranous labyrinth. This is a cross-section of a cat's cochlea. And you can see the scala vestibuli, scala tympani, scala media, Reissner's membrane, basilar membrane, same here, vestibuli, media, tympani. You can see the stria vascularis. You can see the spiral ligament, spiral lamina. So again, all looking at these, and then we highlighted last week too how the basilar membrane and the whole scala media gets wider and wider toward the narrow apex of the cochlea, going exactly backwards to the way you'd think. So an unrolled cochlea, if you unrolled it, it would probably be about 3 centimeters in length, the whole thing. But notice the oval window, round window at the base, wide end of the cochlea, and then the narrow end, the apex, and yet the scala media gets wider toward the apex. Remember the array of hair cells we described last week too. 1 row of inner hair cells all the way along, and then 3 rows of outer hair cells here, 4 rows here, and 5 rows of outer hair cells here. How many inner hair cells do you have in each cochlea? 3,000. How many outer hair cells? 4,000. I should say 12,000. I don't know where I'm getting 4 from. 12,000. Okay, so never think just because you see one row of inner hair cells and 3 rows of outers, as you commonly do in pictures. 3 times 3 would be 9. You know, you'd think you'd have 9,000 outer hair cells, but you have 12. And it's because you get 4 rows over here and 5 rows over here. So showing you this picture as well. Now back to the rolled section or cross section of the cochlea. This picture would be much like this one here. Okay, just showing you in more of a pictorial way, I guess. And notice again, the scala media gets wider and wider as you go toward the apex. And notice the hair cell region would be right where my cursor is. Right where my cursor is. Right where my cursor is. Basilar membrane, Reissner's membrane, spiral ligament, stria vascularis, tectorial membrane, what do you call it, spiral ganglia. Here I guess you would have sort of the spiral lamina, but I'm not showing you that much in this picture here. Now before we move any further, let's go into our notes and make sure we are all together here. So the vestibular system we covered last week. We'll just carry on. Bottom of page 1. And here you get to some specifics. Well, still it's gross anatomy. Remember, 2.5 turns to the human cochlea. Chinchilla cochlea and some animal cochleas have more turns. Remember, it's about the size of the tip of your pinky. Human cochlea is remarkably inaccessible, buried inside the hardest bone of the body, the petrous portion of the temporal lobe. Contains a bony labyrinth which is filled with perilymph. And of course a membranous labyrinth. This ductus reunions is simply the communication of endolymph between the vestibular system and the cochlea. Don't worry about that. Scala. Okay, scala vestibuli, bony labyrinth. Contains perilymph. Associate with the oval window. Scala tympani, also bony labyrinth. Contains perilymph. Associate with the round window. Scala media, the membranous labyrinth, filled with endolymph, contains the hair cells and the whole organ of Corti. The organ of Corti is what we're going to look at closely now. We're going to move in to look at that in more detail. And of course the helicotrema, la 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 la, which is the small hole at the apex of the cochlea which connects the scala vestibuli to scala tympani. In other words, the fluid has to be able to move through that. That's how the perilymph of the scala vestibuli is shared with the perilymph of the scala tympani. Note the location of the bony and membranous labyrinths in relationship to the helicotrema. Let's look at it. Again, make it larger. Helicotrema. Bony labyrinth, perilymph, perilymph. Helicotrema is not really drawn here. You can't see it. But bony labyrinth, scala tympani, bony labyrinth, scala vestibuli, membranous labyrinth, scala media. And before we look here, well, I can see what's wrong with this picture. We covered that last week. The scala medias don't tend to get any bigger as you go toward the apex, but here's a nice picture of the helicotrema. I like this picture showing you the motion of the fluid, and around, and around, and down, down, and around to bulge the round window. There's that interchange, that interplay. This picture is also erroneous. It's a cross section again, but again, the scala medias are largest at the base, which is patently false. Now here we're getting a nice close-up of one of these coils. So we're looking at one of these closer up, okay? Or to be more accurate, this one here closer up. Or in my picture, you're looking at this closer up. Okay, and notice the main pieces and parts. The main pieces and parts. What you have: scala, bony labyrinth, scala vestibuli, containing perilymph. Bony labyrinth, scala tympani, containing perilymph. Membranous labyrinth, scala media, containing endolymph. Memorize the 3 scalas, or spirals. Spiral ligament, spiral lamina, look where my cursor is, and spiral ganglia. The gang of cell bodies of the 8th nerve. You have one tentacle of the 8th nerves going this way toward the hair cells, and of course the rest would continue on toward the brain stem. And the 8th nerve is about 1 inch long. But the cell bodies are located in the spiral ganglia. And don't think you just have 1 spiral ganglia, because you don't. Look. And don't think you have 5. Remember, you're going around. Okay, it's you have hundreds of them going around and around and around. So always remember that, because what you're looking at here is a cross section. This is a cross section, like you sliced this down the middle. Okay, if you sliced it down the middle and turned it toward you, it would look like that. And here you happen to see 5 spiral ganglia here because it's sliced down the middle. Okay, always remember that carefully. Remember your 3 membranes: Reissner's membrane, tectorial membrane, basilar membrane. Stria vascularis. Okay, looking closer now. Reissner's membrane, stria vascularis, spiral ligament, basilar membrane, tectorial membrane, spiral ganglia. And look at all the other cells. These are just supporting cells, right where my cursor is moving. Supporting cells, inner hair cell, outer hair cell, outer hair cell, outer hair cell, supporting cells. So all of the supporting cells, tectorial membrane, hair cells, basilar membrane, right what I'm circling here. All of that is the organ of Corti. So now let's go and look at our notes and follow carefully, because what we did was, I believe last week we got to the got through page 2, the gross anatomy of the organ of Corti. Next week begin with a close-up of single turn of the cochlea, bottom third of page 2. So if you're looking at page 2 here, bottom third, close-up of the single turn of the cochlea. So make sure you have these guys all down. And what is the modiolus right here? What the heck is that? Well, when you look at the modiolus, that is going to be the bony core right here, the bony core center of the cochlea. The bony core center of the cochlea. Okay, to the notes. Spiral lamina. Move on down. And the spiral lamina and the spiral ligament, these 2 guys, this one here and this one here, what do? They hold the basilar membrane tight between them. Spiral lamina, spiral ligament, holding the basilar membrane tight. When you think about the basilar membrane, think of it as the floor upon which the hair cells stand. Okay, the floor upon which the hair cells are standing. Top of page 3. Close up of the scala media. So now we're going to look at it much closer. Here we go. You've got this area here. We'll blow it up larger. Moving to here. Now you can see once again, tectorial membrane, outer hair cells. See where the hairs of the outer hair cells are touching the underside of the tectorial membrane. The hairs of the inner, here's the cell, here's the hairs. Internal, external, inner, outer hair cells. Tectorial membrane, don't worry about the names, Henson's, Claudius, reticular lamina, don't care. Limbus, don't care, okay? Rods and tunnel of Corti, don't worry about it. Dieter cells, don't worry about it. It's the outer hair cells, inner hair cells that you've got to really look at. Now we're looking even closer. We're looking at this section here and bringing it closer. Now here we go. You have the tectorial membrane, and this picture is technically inaccurate because the hairs of the inner hair cells do not normally touch the underside of the tectorial membrane. Okay, they almost do, but not quite. Next week, when we focus more on cochlear physiology, we'll discover what the outer hair cells really do, because they do something. They pull this membrane down, they stretch and shrink, their bodies stretch and shrink. They pull this tectorial membrane down so that it can touch the hairs of the inner hair cells. And it's when the hairs are bent or sheared, okay, it's when these hair cells get bent, that sends a current up the eighth nerve. And notice it's the inner hair cells that mostly feed the eighth nerve. These nerve fibers aren't really part of the eighth nerve. They're part of a nerve going to the outer hair cells. Like from the brain. The outer hair cells get info from the brain. The inner hair cells send info to the brain. It's a two-way street. Okay? Anyway, look at all your supporting cells. Outer hair cells, inner hair cells, and the fluid around here would be what? Endolymph. Endolymph. See where I'm circling? So that fluid, follow my cursor, crawls underneath and bathes the hair cell, the stereocilia, not the hair cells' bodies, and fills this area. Okay? But what is surrounding the hair cells? Look at how they're pinched off. Can you see how the tops of the cells are literally pinched off? This picture will show it to you. It has the hair cells removed. You see how these look like golf tees? So the hair cell would be sitting right in here. The hair cell would be sitting right in here. The hair cell would be sitting right here, and the inner hair cells would be right here. But note well that the cell bodies are pinched off from the hairs. Okay, really note that, because the hair cell bodies themselves are surrounded by perilymph again. Yet the stereocilia, or hairs, are surrounded by cortilymph. Now this is really, really, you need to have this. I'll stop sharing for a second. You gotta have this, because otherwise, how does a battery work? It has opposites to it, right? The metals in the battery are different and they create an electrical charge, or there's fluids in the battery that are very different from each other, that create an electrical charge. And that's what the cochlea's purpose is, to create an electrical charge. See, the outer ear gathers sound and sends it to the middle ear. The middle ear transduces or changes that into mechanical energy, pushing the footplate of the stapes in and out of the oval window. This creates fluid movement in the cochlea, and the hair cells take that fluid movement and they change it into electrical current and send that up the eighth nerve, because it's all about electricity. Your brain runs on electricity. And the purpose of the hair cells is to transduce or change hydraulic fluid energy in the cochlea into electrical energy, because electrical energy is the language that the brain understands. Okay? And the only way the hair cells can do that is if they are in contact with two different fluids. And the only way they can be in contact with two different fluids is if the stereocilia are bathed with endolymph, but the cell bodies are bathed with perilymph. So let's look at this and how this works in a picture. Share screen so we can see it more better. All right, I'll go back a couple of slides. All right, and even back. Endolymph, perilymph. Now look where my cursor is circling. How would hair cells be able to touch that? Well, they can't. How would hair cells be able to touch the perilymph in the scala tympani? They can't. So the trick is to lock a little bit of perilymph right here. inside. And that fluid, they call it cortilymph. This is all the organ of Corti, and they call the fluid that surrounds the cell bodies, not the stereocilia, not the hairs, the cell bodies of the hair cells. That perilymph is called cortilymph. Okay? And here too, perilymph out here, perilymph in the scala tympani, endolymph in the scala media, and it can surround, follow my cursor, surrounds the hair cell, I should say the stereocilia of the hair cells, but the cell bodies of the hair cells are surrounded by perilymph, locked inside the organ of Corti, and that perilymph is called cortilymph. Looking at it here as well, endolymph all here, endolymph here, cortilymph surrounding the cell bodies. Endolymph all out here, endolymph where my cursor is moving right here, cortilymph surrounding the cell bodies. And the endolymph and perilymph, or I should say the endolymph and cortilymph, are locked away from touching each other because the cell bodies are literally pilloried or tied around their necks, locked off. That's how the cell bodies, the fluid around the cell bodies does not get in contact with the fluid surrounding outside the cell bodies. Okay, here's a picture showing you the tectorial membrane made, what do you call it, transparent, so that you can see how it's laying over top of the stereocilia of the outer hair cells, and how it's not quite contacting the stereocilia of the inner hair cells. So you have the outer, this one isn't seen because this hair cell's further in, outer hair cell, inner hair cell. And notice that the inner hair cells are wider, they're fatter, they're kind of shaped like pears, whereas the outer hair cells are longer, they're shaped like test tubes. So simple intuition should tell us that when things look different, they probably do different things. So let's look at that here. This is a close-up of the organ of Corti that I just drew. Tectorial membrane on the top. Inner hair cells. Look at how they're rounded more, like shaped like pears. And the hairs don't quite touch the underside of the tectorial membrane. And the outer hair cells, shaped like test tubes, their stereocilia do touch the underside of the tectorial membrane. And notice how I label this, afferent fibers, in other words, eighth nerve fibers, sending info to the brain. Efferent fibers, which come from a nerve that's not the eighth nerve, but runs right alongside it. And that nerve is called, and I would jot this down, olivocochlear bundle. Olive, like an olive, like you're going to eat some olives, okay? Olivo, O-L-I-V-O, dash, olivocochlear, C-O-C-H-L-E-A-R, bundle. That's a nerve that has way fewer fibers than the eighth nerve. It's not as big of a nerve, but look at it. It innervates a lot more hair cells. So here we must be at the base of the cochlea because we've only got 3 rows of outer hair cells shown here, okay? Inner hair cells, there's always 1 row all the way up, remember that. Outer hair cells, there's 3 rows at the base and 5 rows at the apex. This must be at the base of the cochlea too, because as you move toward the apex, you'll get 4 and then 5 rows. But always remember 1 row of inner hair cells. Now here's an actual picture of a human cochlea. Okay, the person died, but look what they're showing you. Scala vestibuli, perilymph, Reissner's membrane, scala media, stria vascularis, SV, spiral ligament, basilar membrane, tectorial membranes pulled way back here. It's no longer laying on top of the outer hair cells. It has atrophied and pulled back. Spiral lamina, and then spiral ganglia. And a picture here. This is just sort of a schematic, okay? Bony labyrinth, membranous labyrinth, bony labyrinth, scala vestibuli, scala media, scala tympani, stria or spiral lamina, spiral ligament, basilar membrane. Tectorial membrane would be this white area here laying on top of the hair cells, outer hair cells, inner hair cells, supporting cells. Stria vascularis, Reissner's membrane, basilar membrane, lots of repetition, making sure that we've got this. Looking closer, or here's the outer hair cells and inner hair cells now. Inner hair cells, notice how you've got a whole bunch of stereocilia on one cell, a whole bunch of stereocilia on another cell, a whole bunch on another cell, a whole bunch on another one. So you've got one hair cell, another hair cell, another one, another one, another one. On top of each inner hair cell, you have 50 stereocilia. Outer hair cells, showing you 3 rows again. One outer hair cell, another outer hair cell, another outer hair cell. Each outer hair cell has 100 stereocilia, and they are arrayed much like V's or horseshoes, whereas the stereocilia on the inner hair cells are not. Now, if I stop sharing for a second, let's look at the notes and make sure we're following right along with our notes. Here we go. Close-up of scala media. I'll make the notes a little larger. Organ of Corti contains hair cells and supporting cells. Its floor is the basilar membrane. The basilar membrane is narrower, has less mass, and is more stiff at the wide base of the cochlea. And yet, conversely, it's wider, has more mass, and is less stiff at the narrow apex of the cochlea. Got to show you here because this will help tie some things together. More mass here, less stiff. Less mass here, more stiff. What have you learned in acoustics? What does mass resonate with? Low frequencies. What does stiffness resonate with? High frequencies. That's why high frequency hair cells are at the base, low frequency hair cells are at the apex, because those are the areas that resonate with the different frequencies. And so the cochlea is tonotopic, T-O-N-O-T-O-P-I-C, tonotopic. Specific frequencies are represented in specific places, just like keys on a piano. Okay? Hair cells are located all along the scala media, but it's the high frequency hair cells that are stimulated with high frequency sounds at the base of the cochlea. Low frequency hair cells are at the apex of the cochlea. Very, very, very important to remember. All right, move along, and let's go to our notes. Tectorial, recall from acoustics. Mass resonates with low, stiffness resonates with highs. We will return to this in physiology next week. Tectorial membrane, a gelatinous mass on top of the hair cells. The tops of the outer hair cells are embedded in it, not the inner hair cells. Their stereocilia do not touch it. Supporting cells, all these weird names, don't memorize them, please. They're just supporting cells that hold the hair cells in place. Put a star by cortilymph. That's the fluid inside the organ of Corti. And it fills the space of Newell and the tunnel of Corti. What the heck is that? Let's see it. I'll show you. Here. The space of Newell, tunnel of Corti, all of that stuff, okay? That's what I mean. Stuff locked inside. All right. Oh, by the way, this is damaged hair cells. Normal hair cells, damaged hair cells. And which ones are damaged most? The inners or the outers? It's mostly the outers. Outer hair cell damage, okay, is the most common cause of hearing loss in the world. Back to our notes. So this section right here where it says cortilymph, make sure you have that. Don't worry about memorizing which one's highest in sodium and lowest in potassium. That kind of stuff, I don't care. That Na, low K, don't worry about it. But cortilymph is like perilymph. It surrounds the cell walls of the hair cell bodies. Endolymph, however, surrounds the stereocilia or hairs. Opposite charges create a huge electrical charge, opposite fluids, creates a huge electrical charge like a battery. Now, electron microscopy of normal versus damaged hair cells. So let's look at electron microscopy. Normal hair cells, damaged hair cells. Inner hair cells, outer hair cells. Inner hair cells, outer hair cells. And looking now, see this plate here? That's what I was saying. The hair cell bodies are separate. Here's the cell bodies, and there's the stereocilia. So the stereocilia are bathed and surrounded by endolymph. The cell bodies are bathed or surrounded by perilymph inside the scala media, which is called cortilymph. So you can see how this plate here just separates the hairs, okay? And I'll show it to you just another way. Separates the hairs from the cell bodies. Okay, I really want to emphasize that. Good. Share screen, back to here. All right. Here's what you're looking down at an inner hair cell. Here's the inner hair cell, here's its stereocilia. Short ones in the front, taller choir boys in the back. Okay? Here's an outer hair cell and its stereocilia. Shorter ones in the front, taller ones toward the back. Here's a human hair. Here's a hair cell. Here's the stereocilia on top of the hair cell. Okay, so the relative sizes of these things. Never think of these hairs as like hairs on a human head. They're totally different. They're just called hair cells because they kind of look like hairs. Here's my buddy, a bug, blown up under an electron microscope view. It's holding a gear in its claw. If we bring that gear closer, you'll notice a tiny little white dot on one of the teeth of the gear. If we bring that closer yet, you'll see it's a hair cell. Don't think of this as one hair. It's probably 100 hairs all clumped together because the hair cell is dead. Okay? Anyway, here's we're looking at if you laid the basilar membrane out, you'd have high frequencies at the base and lower frequencies toward the apex. Again, here's the cochlea all wound up, low frequencies toward the apex, high frequencies are stimulating hair cells near the base. Now let's look at our notes here. Oh yeah, here's another picture. I like this picture too. High frequencies at the base, low frequencies toward the apex. Now we can stop sharing. Let's go and look at our notes. All right, let's make sure we have our numbers correct. Hair cells consist of a cell body and stereocilia standing on top. Inner hair cells, the stereocilia are all arranged like a straight line. Outer hair cells, the stereocilia are arranged in horseshoe patterns, with the tallest ones toward the stria vascularis, or just say the tallest ones toward the back. They look very different from each other. They do vastly different things. More about this in physiology. Remember, anatomy is just what it looks like. Physiology is what it does. Inner hair cells are shaped like jugs. You got 3,000 of them. Put a star by this. All the way up from the base to the apex in one row. 50 stereocilia on top of each one. The tips of the stereocilia are not embedded in the underside of the tectorial membrane. The outer hair cells, on the other hand, are shaped like test tubes. You got 12,000 of them. 3 rows at the base and 5 rows at the apex. About 100 stereocilia on top of each outer hair cell. And the tips of the stereocilia are embedded in the underside of the tectorial membrane. The cochlea is tonotopic. Specific frequencies are represented in specific places. That's what that word means. Think of the keys on a piano. Specific frequencies in specific places. The guy named Helmholtz. Helmholtz was a guy in the 1800s who discovered that the cochlea was tonotopic. He's the one that discovered that high-frequency hair cells would be located at the base and lows at the apex. And he's the one that described the basilar membrane having more mass at the apex and less mass at the base. And therefore, that lows would stimulate the apex and highs would stimulate the base. There's another theory of how we encapsulate pitch. It's called the temporal firing theory, but we won't think about that one so much now. It's the Helmholtz place theory. The cochlea is tonotopic. Hair cells and afferent-efferent pathways. The eighth nerve, remember, is a sensory afferent nerve. As such, it's mainly in cahoots with the inner hair cells. Recall its cell bodies are located in the spiral ganglia of the cochlea. Olivocochlear bundle, on the other hand, consists of efferent fibers, and they run right along the eighth nerve, but it's mostly in association with the outer hair cells. Efferent is from the body to from the brain back to the body. And that's kind of what the outer hair cells are like. They're like muscles inside the cochlea. Basically, a preview of where we're going next week. Outer hair cells help the inner hair cells pick up soft sounds. Outer hair cells help the inner hair cells pick up soft sounds. If 10 dB stimulates the ear, the inner hair cells won't pick it up. 20, they won't pick it up. 30, they won't pick it up. 40, they won't pick it up. 50, maybe. 60, yep, they'll pick it up. 70, yep, they'll pick it up. 80, 90, 100, no problem. The inner hair cells just cannot by themselves sense sounds below 50 decibels. They need the outer hair cells to motorically and mechanically help them do this. And we'll talk about how that works next week in physiology. Suffice to say right now, most damage occurs to the outer hair cells, leaving the individual with an inability to pick up sounds below 50 dB. So the person will have like a 50% hearing loss, a moderate degree of hearing loss due to hair cell damage. It's called sensory neural. Nothing wrong with the eardrum, nothing wrong with the middle ear. It's the outer hair cells are damaged, so now the inners cannot pick up sounds below 50. The guy has a 50 dB hearing loss. And where is that happening most? At the base of the cochlea, where the treble hair cells are located. Trouble hearing treble. Okay? The person will have a 50 decibel hearing loss at 2,000, 4,000, and 8,000 hertz. That's presbycusis. Presbyterian, Church of the Elders. Presbycusis, hearing of the elders. It's all about hair cells. Hair cells rule. 95% of hearing loss is due to outer hair cell damage. 95% of hearing loss is mild to moderate. Mild in the low frequencies, moderate in the high frequencies. The hearing loss audiogram will look like a hill. The low frequencies are up near zero. The high frequency hearing levels are down at around 50. Common, Mr. Jones, Mrs. McGillicuddy, 75 years old. One person in two who's 75 plus has that kind of hearing loss. It's as common as the day is long. All right, let's see where we've come to in our notes. Share a screen. What do we got? All right, we're on page 4 here. And we're just about ready to bag it here. Here you go, that's all that's left. Okay, efferent, olivocochlear bundle messages course or move in the opposite direction to the afferent eighth nerve. Now make sure you've got this in English, okay? Look at it very carefully here. Oops. Go back here, make sure we've got this. Maybe this one will show it too. Let's see. See how the inner hair cells are talking to the eighth nerve. Okay? This part, this nerve here, is innervating the outer hair cells. The outer hair cells. Olivocochlear bundle. Again, let's make sure. Olivocochlear bundle, eighth nerve. They run together. Birds of a feather, but they're different birds. Eighth nerve is coursing from the inner hair cells to the brain, afferent. Olivocochlear bundle is going from the brain stem to the outer hair cells, so that the outer hair cells are given a message to pull the tectorial membrane down so it can bend the hairs of the inner hair cells. And that's why this picture is a little bit inaccurate, because maybe it's showing the outer hair cells having already pulled that membrane down so the inner hair cells can pick it up. Okay, but at any rate, the message is all of this stuff happens really, really fast, like tremendously quickly. And that's why outer hair cells die before inner hair cells. They're the moving part. They're the ones that are always kicking into action, stretching and shrinking, pulling that membrane down, the tectorial membrane, so it can bend the stereocilia of the inner hair cells. We will look much more at that next week. Physiology. Inner hair cells are afferent. They send info from the cochlea to the brain. They comprise only about 20% of all hair cell population, but they get like 95% of the eighth nerve fibers. Each inner hair cell gets about 10 eighth nerve fibers. And these synapses are completely touch directly the bottom undersides of the inner hair cells. Yet, several inner hair cells will share a single olivocochlear bundle fiber. So look at this innervation pattern again. I'll blow it up. Each inner hair cell is going to get about 10 fibers here. Outer hair cells will share, about 10 outer hair cells will share 1/8 nerve fiber. And then each outer hair cell gets lots of olivocochlear bundle fibers, but inner hair cells get hardly any of those. So let's see if we got a picture I can show you there. I might, maybe yes, maybe no, maybe rain, maybe snow. There you go. Yep, look at this. Here's the spiral ganglion. Here's inner hair cells, outer hair cells. Okay, the outer hair cells are mostly olivocochlear bundle is touching those, and they're sending the info to the brain. Okay, and the olivocochlear bundle has only 1,800 fibers. There's not many. Think of nerves like a rope. A rope is made of many, many, many fibers, right? Okay, look at the eighth nerve. It's got tons of fibers, and each inner hair cell gets 10 eighth nerve fibers. So how many inner hair cells do you have? 3,000. How many fibers are there then in the eighth nerve? 30,000. Buku. All right? Lots. Here's noise-induced hearing loss. The guy's got good hearing in his left ear. You can see at 0 decibels, no problemo. He can hear about 0 to 10 decibels. And then he's got a high-frequency hearing loss. Way up in the high frequencies. And look at the hair cell count. What they did was when he died, they opened him up and they examined the basilar membrane, and they noticed where the hair cells were living and where they were dead. Okay? And it's near the base of the cochlea, high frequency hearing loss caused by noise. Here's a hunter who died who was right-handed. And when you're right-handed, you're holding a rifle this way. And so my left ear is mostly going to get the loud sound. So in right-handed hunters using rifles, they'll get more noise-induced hearing loss in the left ear. Left-handed hunters, they'll get more noise-induced hearing loss in the right ear. And that's exactly what is shown in this picture here. Oh, here. So if it's like there, good. The right ear of the left-handed hunter, I should say of the right-handed hunter, hair cell, inner hair cells, a little bit damaged. Outer hair cells, a little bit damaged right here at this frequency, mostly there. You're looking at his left ear, inner hair cells, no problem, no problem, no problem. All of a sudden they're dead. Outer hair cells, living, 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 dead. Okay? Near the base of the cochlea, high frequency hearing loss, way worse. So when they actually opened up his ear, his cochleas, and looked in, you could see the hair cell death. They unrolled the basilar membrane, and they just looked at where the hair cells were dead, mostly in the high frequencies, especially for his left ear, because it's the left ear that's closest to the what do you call it, to the noise of the rifle. See, there's this high frequency hearing loss. Noise-induced hearing loss, by the way, is the second most common cause of hearing loss. After presbycusis, aging, it's noise. Noise-induced hearing loss is the most preventable hearing loss as well. But we live in a noisy society. Americans have more noise pollution than Africa does. So elderly in United States have a kind of a combination, especially men, of presbycusis and noise-induced hearing loss from working in noisy environments. Whereas elderly in Africa don't have as much noise pollution because there's less industry there. They'll have simply presbycusis, but not the added component of noise-induced loss. Noise-induced hearing loss, you will learn in disorders this summer when you take HEAR, when you take 125. Noise-induced hearing loss always has this notch in it. I'll show you. Always has this notch at 4,000 hertz. And you know why? It's because of the outer ear canal resonance that we described in 110 acoustics this morning. The outer ear resonance helps us hear the soft high frequency consonants. Oh yeah, that's a blessing, but it's a curse when it comes to noise, because the noise will be found also at those high frequencies. And so the hair cell damage will mostly occur there. This is how you notice noise-induced loss. It's that notch of hearing loss, especially at 4,000 hertz. Okay, it really hurts. So if we go now to the notes and finish off here, outer hair cells are mostly efferent. They send info from the brain back, or they receive info from the brain back to the cochlea. 80% of the hair, all hair cells are outer hair cells, but they barely get any eighth nerve fibers. They mainly are in cahoots with the olivocochlear bundle fibers. Afferent hair cell feedback loop. Afferent root, inner hair cells to eighth nerve, to cochlear nucleus in your brainstem. Efferent root, brainstem. Look at the superior olivary complex. Superior olivary complex. Olives, you think of olives with a pimento. No, in your brainstem. What's the brainstem? Your spinal cord inside your skull. Okay? And you're in your spinal cord inside your skull. It's about the thickness of my finger, maybe a little bit more like my pinky. And the brainstem is about as long as my pinky, about a little over an inch. Okay? You got 12 pairs of cranial nerves coming off of it. The eighth pair is the auditory nerve, the eighth nerve. So you have one for the right ear, one for the left ear. But inside the brain stem are nuclei, little gray areas of cell bodies. And one of these areas is called the superior olivary complex. It's buried inside the brainstem. So the eighth nerve goes and touches the brainstem, and then inside the brainstem, you've got messages going on, and from those superior olivary complexes, we'll learn more about them later in this course, okay? I'm just giving you a heads up now. From inside of that brainstem, there's a nucleus area called the superior olivary complexes. And the nerve running from those is the olivocochlear bundle. That's why it's called the olivocochlear bundle. It's running from the superior olives to the cochlea, olivocochlear bundle. And to where in the cochlea? The outer hair cells. So you've got this afferent loop, efferent loop. Afferent, inner hair cells, eighth nerve to brainstem. Efferent loop from inside the brainstem, superior olivary complexes, olivocochlear bundle, ending on the outer hair cells. So think of how fast those messages have to be moving constantly. So your outer hair cells are constantly getting messages. If it's a soft sound below 50, shrink, pull the tectorial membrane down to stimulate the inner hair cells. If the sound's over 50, don't. So you got moving parts inside the cochlea, and those moving parts are the outer hair cells. So remember the numbers of outer hair cells, 12,000. The number of inner hair cells, 3,000. Inner hair cells looking like jugs, outer hair cells looking like test tubes. 50 stereocilia on top of each inner hair cell, 100 stereocilia on top of each outer hair cell. The cortilymph stuff we've talked about, the finer anatomy of the organ of Corti, basilar membrane, spiral ligament, spiral lamina, Reissner's membrane, supporting cells, stria vascularis, outer hair cells, inner hair cells, endolymph in contact with the stereocilia of the hair cells, cortilymph in contact with the cell bodies of the hair cells. Good. Lots there, lots there. Share, we're everywhere. We're just about done today. Go to our PowerPoints here, and sure enough, this would be it. That's the end of the PowerPoints. This is the end of the notes. So there is your stuff on inner ear anatomy. So highlight the areas, very importantly, the ones to memorize and understand. Don't worry so much about this, supporting cells. Basically, look at it from the top like this. I got a couple of minutes left in this hour, so let's just highlight the areas we really should know. Always digest these notes carefully. Don't think that you have to don't make it a jumble. As I say, when you're sitting down to eat, you don't throw the whole plate against your face. You eat with a fork, and you take one bite at a time. First, digest this. Make sure you know that. It's shared, okay? There's bony labyrinths in the vestibular system and the cochlea. There's membranous labyrinths in the vestibular system and the cochlea. There's endolymph and perilymph in the vestibular system and in the cochlea. There are afferent and efferent hair cells in the vestibular system and in the cochlea. Get it? Good. Vestibular system, be sure you know that the utricle and saccule are part of the membranous labyrinths and that they help you detect linear acceleration to and fro and up and down, and that the semicircular canals are part of the vestibular system, and they are located in 3 orthogonal planes, as I said last week, much like this corner I'm pointing at back here. You got the ceiling and the 2 walls meeting at 90-degree angles to each other. And what is the main purpose of the semicircular canals? To help you notice when you're turning around a corner, and also so you can notice where your head position is in space. Because no matter how they are placed, okay, I've got 3 dimensions. This is the floor, here's 1 dimension, and then my palm is another dimension. No matter which way I move, hair cells are going to get stimulated in one of those areas, in one of those 3 semicircular canals. What's the main pathology of the vestibular system? Benign paroxysmal vertigo, BPV, and you have that in the notes as well. All right, very, very common pathology, BPV. And electronystagmography is a test that audiologists do to detect pathology of the vestibular system. Now you're getting into the cochlea. Realize it's got 2.5 turns. that it's remarkably inaccessible because it's buried in the petrous portion of the temporal bone. Notice the three scalas. Okay, scala tympani, vestibuli, and media. Know which one is the membranous labyrinth and which ones are bony labyrinths. Notice that the scala vestibuli and tympani, bony labyrinths, are connected to each other by way of the helicotrema. Then you have a close-up of the cochlea of the membranous labyrinth itself. Memorize the pieces and parts. There you go. And looking at it very close up, we looked more at the tectorial membrane and how it touches the tops of the outer hair cells, but not the inners. We told you to ignore this part, but we said concentrate, make sure you don't forget the cordylymph, and then memorize the stuff about the hair cells. How many parts and pieces, how many you have, how many stereocilia, how many rows, and that the cochlea is, of course, tonotopic. That's all for me, folks. That's all for today. We will stop sharing here, and I'll stop recording here. This has been 120, February 26, 2019. We have now finished the anatomy of the inner ear. For 2 weeks, we will be looking at the physiology of the inner ear, how it works. We alluded a little bit to that now, but we'll look at that much more in earnest in the next couple of weeks. And then after that, we'll look at retrocochlear stuff. We'll look at the eighth nerve. We'll look at the olivocochlear bundle. And last of all, we'll look at the auditory areas of the brain, known as the temporal lobes, the sides. Okay? All right, I'll stop recording here and end the session and grab another coffee. Cheers.